Okay. So this is the 8th problem. It says the block of mass m is placed on top of a hole in a horizontal table. This is the hole. A spring of force constant K is connected to the block through the hole. The other end of the spring has a particle of mass small m connected to it. With what maximum amplitude can the particle oscillate up and down so that block does not lose contact with the table? Okay. So here this say this is the mean position of the block. Block means this particle. So this is the mean position. Achha. So the spring is already in extended state. So suppose this is the natural length or the free length. This much is the free length of the spring. So the extension in the spring is equal to x naught. So that x naught equal to mg divided by k. Now this block will lose contact with the table when the spring force, the compressive force on the spring, compressive force of the spring on the block upward will be equal to this weight capital Mg. Now this compressive force will act when this is the extreme position. This is the extreme position of small m, oscillation of small m. So mean to extreme means the amplitude of oscillation. So this is A. Okay. Now while this is at the extreme position, then what is the compression in the spring? The compression in the spring is equal to A minus x naught, right? This A minus x naught. So A minus x naught is compression in the spring when small m is at the upper extreme. Then the compressive force acting on the block will be, compressive force is K multiplied by A minus x naught, and the downward force will be mg, and these two will balance. Therefore mg equal to K into A minus x naught gives you, so what we have to find out? Amplitude. So amplitude equal to mg by k plus x naught. Therefore amplitude equal to mg, capital Mg by k plus x naught. Now x naught is equal to this small mg by k. Now this is problem number 9. It's given that two small balls, each of mass small m, are connected by a light rod of length L. The system is suspended from its center by a thin wire of torsional constant K. That means this wire has got a torsional constant K. The rod is rotated about the wire through an angle theta naught and release. Find tension in rod as the system passes through the main position. Now we will see the top view of the thing. So in the top view, as we see, this is a question on torsional pendulum, and here the angular amplitude of oscillation is theta naught. So it's moved, rotated to this position and released. So this angle is equal to theta naught. Okay, so there will be torsion. So this torsion constant theta means it will be acted upon by this force k theta. Now in this diagram it's moving this way, so this k theta. This torsion equal to minus of k theta with proper signs. Okay, so when it passes through the mean position, so at mean position, after it is released from this extreme position, when it again passes through the mean position, angular velocity is, say, when it passes through the mean position, linear velocity is v. So angular velocity v by half of the length, whatever. So here you can write 2 into half m v square equal to the potential energy stored in the string is converted to this Ke. So it will be half k theta naught square. Therefore you can find v as theta naught root over of k by m, right. So what we have to find at this position, we have to find tension, the force that the rod applies on the blocks, the balls. So at this position, so once again we will move on to the front view. So there is a force F1 applied. This is the rod, this is a long rod from where it is suspended. So here the force F1, this F1 supplies the necessary centripetal force. So we can write F1 equal to m v square by radius of the path is L by 2, right. And also there is weight mg. So the rod will apply a force upward on the ball F2. So F2 is equal to mg. So therefore net force of the rod on each ball is root over of F1 square plus F2 square, and we have calculated V in the previous page. We can substitute its value to get F, right. Let's move on to the next problem. A uniform cylinder of mass small m performs small oscillations by rolling without slipping inside the surface of a large cylinder. So this is the large cylinder of radius R, capital R, and this cylinder, this small cylinder, is rolling without slipping inside the surface. Okay. So the surface is rough enough to ensure that it rolls without slipping. So we have to find its time period. So energy method will be best, I think. So this distance is r minus small r, and this angle is theta. So angular oscillations. So velocity of the center of mass of the cylinder V equal to r minus small r into d theta dt, or we can write as r minus small r into theta dot means d theta dt. So and also the center of curvature we can take as a reference for calculating gravitational potential energy. So total energy E equal to minus of m g r minus r plus kinetic energy, translational kinetic energy is half m r minus r square theta dot square, and rotational kinetic energy is half m r square. Now this is v by r square. See, the angular velocity of this cylinder, so as we know, this is the instantaneous axis of rotation, IAOR. So angular velocity is this v by this distance r, right? So therefore again we can write E equal to minus mg r minus r plus half m r minus r square theta dot square plus square will cancel 1/4 m v square, and we'll substitute this. So as this E is constant with time, we can differentiate with respect to time. You get 0 here, and oh sorry, I missed out this cos theta, right? I mean the height, this height is cos theta. All right, here cos theta. So you get minus mg r minus r. Now cos theta, if you differentiate, you get sin theta. As it's small, I replace it by theta, and again theta dot comes in plus half m r minus r square. Now 2 theta dot into theta double dot plus 1/4 m r minus r square, again 2 theta dot into theta double dot. Now after simplifying this, you'll get a, see the calculations you do yourself, right? So there you get a theta dot will cancel, so theta double dot means this d2 theta dt square equal to, it will be of term this form, minus some constant into theta, so we'll write that minus omega square times theta. This omega is the angular frequency or of the angular SHM, right? So that time period we can find out 2 pi by this omega.